Okay, so this is not that computer I'm controlling. Okay, so this is lecture 9, slideshow from the current slide. When we left off last class, we're going this way. We had just done making a disaccharide using a glycal activated by IDCP. And so I'm not going to spend too much more time on glycals, but I am going to spend today. We're going to talk a little bit about the options we've got with the halogens and why this is kind of handy, and then what we can do with epoxides for these instead of halogens. So the thing that we should note here is we iodinated the top face. We used IDCP. If we had chosen to use NIS, we would have gone for the bottom face. We got we got the bottom face with IDCP. If we had gone with NIS, we would have gotten the top face. There we go. And then we ended after the iodonium ion, which was A. We ring opened that with an alcohol, attacked the anomeric center, and because the iodonium was on the bottom, it attacked beta, which is good. And then we're left with an iodine at C2. And one thing we could do was we could use acetate in the presence of a little bit of silver salt to do an SN2 on that position. And basically, SN2, yes, that's what I mean to say. And switch to the mannose configuration, so inversion of configuration. Cool. So what we can think of then is, if we want the mannose configuration and we want a beta here, it's easy to get these cis using this strategy. So for example, if we had done a slightly different one, sorry, I'm just gonna, no, bad. So if I used NIS, and iodosuccinimide, structure was a couple of lectures ago, we would have had the up iodine. And then if we had used a nucleophile, and it could have been anything, it could have been a sugar, but just for speed here, I'm going to stick with ethanol, which is like my nucleophile of choice. Just opens the iodonium. And then I can treat that with some silver salt. The silver salt, which silver salt you use, doesn't really matter. What I'm picking is a salt that has a not very good nucleophilic anion. I don't really want silver chloride because chloride is a decent nucleophile. Nitrate's a shitty ass nucleophile. You could have picked silver BF4, silver triflate, any of those non-coordinating, silver sulfate. Any of the non-coordinating ones are pretty good. And acetic acid, sodium acetate. And that's going to come in and it's going to attack SN2 like again. Sorry, there's benzoprotectant groups and everything else that we just can't be shitted to draw. And so what we've got again is these two guys are cis. So we can make alpha glucose galactose or we can make beta mannose using this strategy. But the whole idea here is you have that cis thing going on. But what if you don't want to do cis? What if you want to do trans? Well, you're kind of screwed with this stuff because you're going to be kind of stuck doing it this way. The only way that works a little bit use epoxides. So there is a way that works a little bit using a weak silver salt or a weak Lewis acid to activate it, and you make more of an oxocarbenium. And so you'd have, but we're not going to, you know what? We're not going to cover that. This shit's complicated enough. We're just going to pretend you can't do it. It doesn't work very well anyways, so you'd be an idiot to try it. Just find a different way. This is really good if you want these cis kind of things. And we're going to come back to this in a second. But what I want to do is just stick with these iodine for a moment. So one thing that we pointed out was we can make the glycal with the acetate still present. So this is another way we can get that trend. So if we take this guy, and we treat that with NIS, we get the up iodine. Now, you can't really get anchumeric assistance in this case because now the iodine is kind of forcing this thing out. It really can't reach around anymore because you have this other ring here, and it's just, you can't do the 5 and the 3. It just doesn't work. So this is one of those cases where this is not going to participate. It's about actually, no, it's not one of those things. It is the only time this is not really going to participate. So when I add some ethanol, it reacts exactly as if the acetate wasn't there. We get the same product. Again, trans iodine ethanol. And there's an acetate here. Now, we could displace this iodine by using a nucleophile, but then we'd have 2 oxygens on that carbon, and that's not really a sugar. Or we can just burn that iodine off, and that's maybe what we want to do, is I just want to replace that with a hydrogen. Okay. Acetate still there, hasn't gone anywhere. So all I want to do is burn off that iodine and replace it with a hydrogen. Does anyone know how to do that? This is a dehalogenation reaction. Conceptually, you don't need the precise reagents.
Could you use a hydride?
Yeah,
Like
the
as a
problem. So if you use a
nucleophile?
hydride, often hydrides attack using SN2 chemistry, so you get
Okay.
inversion of configuration.
Okay, so we would want like like a E1
Right,
type
but then
thing.
E1 scrambles, right? You'll get like a 50-50 mixture of things.
Oh, gotcha.
So hydride's a good idea. Just like if we want an inversion, a hydride works great. But we don't. We want retention.
Great. So we would want like an SN1 like mechanism.
We want almost like a double SN2 because an SN1 again scrambles things.
Okay.
Now you could do a double SN2, but there's an easier way to do it. So that's if we take. So this is for any molecule like this. So I'm just going to draw a model compound. This is a model compound. It has nothing to do with sugars. And we retain stereochemistry. The reagents we're going to use is we're going to do a radical abstraction of the halogen. So we're going to radically reduce it down. So mechanistically, we are going to randomly draw lines all over the page. This is a radical dehalogenation. So you add halogens, using radicals to alkyl groups. You can remove halogens using radicals on alkyl groups. Radicals. Who understands them? So AIBN is a radical initiator. It's one of the best ones out there. So at about 65 degrees Celsius, depending on who you ask, this wants to become nitrogen gas, because anything that has two bonds to nitrogen, double bond nitrogen, really just wants to finish it off and make nitrogen triple bond nitrogen and get it all over with and become nitrogen gas, because everything wants to become nitrogen gas in the end. So to help it become nitrogen gas, you heat it just a little bit, and it generates two of these radicals plus nitrogen gas. Radical is pretty good, stabilized by resonance by the cyanyl group. It's a tertiary radical. That's pretty good. This is why it's so favored. AIBN goes in and out of able to ship it to Canada. So there'll be years where I can't get it because they'll say it's going to blow everything up, because it does explode. And like if you get to these temperatures. And then it's easy to get again. And then it gets hard to get again. And it gets easy to get again. What's really funny is the analog. I'm going to just erase this, where these are cyclohexyls instead of isopropanols, are always easy to get, even though they explode at exactly the same temperature. But that's just regulations for you. So I'll keep it like this. So you take that, and like any radical, radicals are always looking for the weakest bond anywhere. That's what radicals do. And so the weakest bond that this radical can find is the hydrogen tin bond. That's a stupid bond anyways. And we generate a tin radical. So organic radicals are rather upsetting. Radicals on metals seem kind of normal to me. Metals often have radicals on them. Currently doing a project where we're using copper to kill COVID-19, and it's all due to, copper basically has lots of radicals, and it, turns oxygen to hydrogen peroxide, which then starts epoxidizing the uh, lipids and proteins in the COVID-19 capsule, and that degrades the capsule, and then the RNA falls out, and then the RNA degrades, and you kill COVID-19. It happens in a few minutes. It's pretty cool. But it's because, metals got radicals. It's kind of what they do. So now that's looking around for the weakest bond, because, again, that's all radicals do, is they look for the weakest bond. It's the only way to think about them. Otherwise, they really make no sense. And the weakest bond, of course, is another one of the same. The problem is that's not productive. We put in a tin radical and tributyl tin hydride, and we get a tin radical out plus tributyl tin hydride. So we're going to look for the second weakest bond. And the second weakest bond is the carbon iodine bond. So this is where the magic happens. And that's that radical is sitting in an sp3 orbital. It's not going p. Lower energy in an sp3 orbital. There's no reason for it to go into a p orbital. So it's going to stay there. And because it stays in an sp3 orbital, it keeps the stereochemical configuration. Like, that doesn't change. So the stereochemical information in the starting material, turn my camera on, I have to look at myself. I don't want to do that. So it keeps the stereochemical information there. The iodine was down. The radical is still down. And that's still a radical. I've just drawn a single electron in orbital. It's okay. I'm going to clean it up because it's really messy. And I'm drawing the orbital going back and away from me. Now that's looking for the weakest orbit thing around, weakest bond around. That still has not changed. That is still the tributyl tin hydride. And we get the tributyl tin radical, which is then ready to go back into the sequence again. So that's how this chemistry works, where, go back to the slide, AIBN, tributyl tin, magic happens, remove the iodine. So if we're thinking about that, there's a few things we can do with that are kind of cool. So if we have, say we just did a glycal reaction, we've got that. We can use the sodium acetate. We can use AIBN tributyl tin. And then what we do is, in this case, we'll just have a deoxy sugar. Like we're not going to have any oxygen or any substituent there. But nothing's stopping us using some other kind of nucleophile. Sodium azide, for example. Which takes us down to that. And so I just posted assignment, I did just post it, assignment 2, and it is going to talk a little bit about using these amino sugars. And that's because having a nitrogen at that C2 position is actually quite a common thing in life, in biology. Glucosamine, galactosamine means the amine is at C2. It's not in a name. It's not clear where the amine is when you say glucosamine, but it's at the C2 position. And so we can take that azide and we can reduce that. There's lots of ways to do it. If you're a better chemist than me, you can use triphenylphosphine, and that will knock it down to the amine. This reaction just never works for me, ever. I've never gotten it to work. Everyone else can get it to work. I am just absolutely incompetent. I have no idea. I can get everything else to work. I just cannot get this thing to go to save my life. This is called a Staudinger reduction. It is the only reaction I have ever failed to get to go, no matter what, and it's really easy to do. Like I have first year undergrad, so no problem with this, and I just can never get it to work, and I don't know what's going on. Oh, I use any other reduction. There's tons of ways to reduce azides. Samurai asked which way do I use? Hydrogen on palladium, iron salts, tin salts, um, transfer hydrogenation using ammonium formate and palladium. Yeah, anything but a Staudinger. Just not Staudingers. Okay, but better people can do this. There's lots of ways to do it. So we have ways that we can sort of burn off that iodine, or we can replace it with things. The other thing to consider is that the glycal is one of the ways that we can introduce a fluorine at C2. And why would we want to do that? Let's say we had a glycal. And, we're used to working with F minus. This reagent is called select fluor, which is a stupid name for a reagent. I have no idea how they discovered this. It does not look safe. So it's kind of like a box. Okay, it does not want me to be able to write that because right at the bottom of the page, it's like, you're off the page. So you have two quaternary nitrogens. One of them's got a fluorine on it, and one of them's got a CH2Cl. And this is one of those things which does not make intuitive sense to me. Like, to me, if you ask me what is the most electrophilic site on this molecule, I'd pick that carbon there, and I'd be wrong. It's the fluorine. And so select fluor is a source of F+. So you can kind of imagine it. Maybe you can't imagine it, which is okay too. Sort of. I'm going to grab the fluorine and put the electrons onto nitrogen. It might be something to do with it being a double positive molecule. That makes that different, and it changes how the methyl and the fluorine work and where the LUMO of the system is, and I clearly don't understand anything. But select fluor works kind of like NIS. Anything else? Sorry, it works like IDCP. And what we're going to do is we're going to put fluorine on the bottom. So then when we bring in a nucleophile, like ethanol, or sugar more likely, we get a C2 fluorine. So why is that useful? Well, fluorine is actually a lot like OH. So fluorine's a lot smaller than OH. It's like the size of hydrogen, but it pulls electron density like OH does, but it's also a lot harder to metabolize. Like, there aren't a lot of carbon fluorine bonds in your body. I'm going to say there aren't any, but I'd be wrong. I'm sure there's something. I'm sure there's some weird ass metabolite that we have somewhere in our liver that has a carbon fluorine bond in it. But fluorine really is not an element that we use in biology. And so when you replace one of the oxygens with fluorine, it confuses enzymes. And so then enzymes get really confused about breaking down these sugars because they've got a fluorine on it. And they're not quite sure what to do with that. It also makes it a lot greasier. So an OH is hydrophilic, interacts with water. The fluorine is polar. It's doing all the same kind of polar thing, but it doesn't interact with water very well. So if for some reason, and we're going to come back to this a little bit later in the course, this is dipping into an enzyme pocket, then suddenly you're switching a hydrophilic component for a hydrophobic component, but the electrostatics of the surface look quite similar. So as far as the enzyme, it looks all the same. So enthalpy wise, the binding is similar, but you have this huge entropic benefit because now you're putting hydrophobic with hydrophobic, and you're able to desolvate. You're taking the water away from a fluorine, which they're not really well attached to anyways, instead of taking them away from an OH that they are pretty well attached to. So you tend to make much stronger drugs by swapping out OHs for fluorines if you don't need the hydrogen bond from that OH. If you need the hydrogen bond, this was a bad idea. But if you don't, this is a really good substitution. So you'll see a lot of that. You'll see a lot of that in medicinal chemistry. Actually, if you look at drugs, there's just fluorines freaking everywhere. So this is a good way to introduce a C2 fluoride is using these glycals. We can also introduce C2 iodides or C2 bromides. Not as useful because they're much more reactive. A carbon-fluorine bond is a lot stronger, much less going on. But if we do make the iodide or the bromide, we can then displace it. We can burn it off, or we can replace it with a nitrogen, which I guess is displacing, but not with oxygen, but with nitrogen. So we have some options with what we want to do with these glycals. So a little bit earlier, I was saying that, look, this is all well and good to make these cis systems. What about a trans system? Well, one way we can make the trans system is we just saw it if we still have the OAC here. That was easy enough to make the trans system. But another way we can do it with just a glycal is we saw this a couple classes ago. I want to make sure I'm consistent with the notes that I used. So I am going back. I definitely showed DMDO on the bottom face, which is correct. MCBBA also on the bottom face, which is also correct. Okay, good. So if I use DMDO, we covered the mechanism a little while back. So you epoxidize trans to the C3 substituent. So we've already talked about that. So this is in the up position here. So the down is H, so the epoxide goes in the bottom. Most times it's going to go on the bottom because most of the time we're using like normal sugars and they all have C3 axial or equatorial. Mannose, glucose, galactose all have C3 equatorial. C3 is not something that any of them play with. So if we take that and we treat that with a weak Lewis acid, and the typical one that gets used is zinc bromide. So we had zinc to make galactals or glycals. Like a galactal is a glycal made of galactose. And my mind always goes to that because galactose is my favorite sugar. So I'm always thinking about galactose. But I meant glycal. So we made glycals using zinc metal. Here we're using a zinc 2 salt, not a zinc 0, a zinc 2 as a Lewis acid. And we'll stick with ethanol. And so we make a dative bond here between so it's strong but not super strong. If you use too strong a Lewis acid, everything kind of falls apart. So that's why we're using kind of a mild Lewis acid. We're not pulling out the TMS triflate or something. And then the ethanol is going to come in, taking its time. And it's going to come in trans because we're not fully breaking that bond. We're not fully making the oxocarbenium because this is under a blank page. That is not what I wanted. I guess technically the zinc bromide is negative here if I've got zinc Br2. So let's just change it to zinc Br. And then everything's neutral. Everyone's happy. So we've got sort of a gentle approach here. And, there's lots of things we can use there as a nucleophile to lead into what we're going to switch into for the next little bit of the lectures. Let's say we had started with thiophenol as a nucleophile.
John, sorry to interrupt. So are you saying that the zinc bromide like becomes zinc one?
It's still zinc 2 here.
Yeah, like at the beginning, we're still using zinc two. Okay.
It's zinc 2 the whole way through.
Okay.
Like if you're more comfortable,
Oh yeah, I'm
I
an
can do
idiot. Sorry.
this.
Yeah, I
That's
can't. I
fine.
can't count.
Like it's kind of soft actually. The reason why it's not super strong Lewis acid is because the zinc isn't so ready to lose those bromides, so it's kind of negatively charged, and that's zinc actually is okay being negatively charged. It's not that unhappy as far as metals go, but it's not desperately looking for electrons the way that like some of these other Lewis acids we've been looking at do. So it's kind of a gentle oxygen zinc bond, very very easily cleavable. You're just you're slowly pulling electron density out of the other oxygen bonds, but you're not pulling that much. I've drawn it as a covalent bond. You could draw it as a dative bond if you're so inclined with an arrow there instead, if you like. I fully accept that and it's completely correct. I just don't like dative bonds. So we can do this with other types of nucleophiles. One of the more common ones to do this with is with sulfur nucleophiles. And we'll see why we're interested in that. But we've got ways to do it that way too. But let's say we're impatient and we don't want beta. So we want alpha, and we have an epoxide, or we have a glycal. And let's say for whatever reason we don't want to use the halogens because we can do that. We've just seen doing that. But we've got an epoxide, and we want the alpha. So if we're going to get the alpha, what we need to do is we need to make sure that we break this bond completely, conceptually, right? Because if that bond's still present, we're going to deliver beta. That's what happened last time. The bond was still present, we deliver beta. But if we can break that bond completely, then we can deliver alpha because of the anomeric effect. So we need a really good way of doing that. And the best way of doing that is to use tin. So tin raises its ugly head again. So again, using ethanol as the nucleophile because I like ethanol. Okay, we got a few things going on here. We've got a tin nucleophile, which is great. Little sidebar down here. How do you make a tin nucleophile? You take a normal alcohol, you treat that with sodium hydride. That's good. You treat that with tin chloride. Well, tributyl tin chloride. Tin chloride is something different. And that just does essentially, it's not quite an SN2. Tin has too many electrons and orbitals. So it's addition. You make a 5-coordinate tin where there's actually 5 bonds and it falls apart. But I'm happy if you want to draw it in one step because this just takes less time. So you can turn any alcohol into a tin alkoxide, I guess. Stannyl alkoxide. There's probably a really fancy way to say that, but tin alkoxide I'll live with. Well, you take that and you mix that with the silver salt, and you know something happens. The tin and silver basically do a salt metathesis, so we switch them out. So I think what you can think of is BF4 dissociates more or less completely. Let's just draw this out. Now I'm being unfair to the poor oxygen tin bond here because that's actually a really strong covalent bond. Oxygen loves making bonds with tin, but oxygen also likes making bonds with silver. And so what we're going to do is we're going to go to a silver oxygen bond and then a tin BF4. Of course, the issue here now is that tin BF4 is non-coordinating. Like it doesn't bind to the tin. So you actually have a tin plus floating around. And it just so happens loves epoxides. Just freaking loves epoxides more than anything. And I don't, it's something to do with the geometry of the epoxides, and I don't really understand this. I don't know why it's preferring an epoxide to an alkoxide. That doesn't make a lot of sense to me, but it does because you see tin salts being used with epoxides all the time to activate them, and it works great. So your epoxide attacks your tin salt. And when that happens, now we've just, I was just saying, I was sort of emphasizing the zinc kind of was there, kind of not. It wasn't a super strong bond. Happy with the data bond, blah, blah, blah. This is a freaking covalent bond. And of course, that means you have a positive charge on oxygen. That sucks. We'll help out a little bit here and try and get a good resonance structure. So we're going to make the oxocarbenium. And in the process of doing this, we have completely broken that C2 bond. Now we're using oxocarbenium chemistry. And all else being equal, you know what? Stuff being a little bit favored, because like ether, THF like sitting beta, our nucleophile is going to come in alpha. We're getting alpha attacked because of the anomeric effect. So, if we just use a weak Lewis acid like zinc dibromide, we don't break the bonds. The epoxide exists until the epoxide gets ring opened by the nucleophile. If we use a very oxophilic, epoxide philic Lewis acid like tin tribromide, tributyl tin, there's no bromine, tributyl tin plus We go through the oxocarbenium. We follow all the same rules of oxocarbenium chemistry. We fall back on solvents and all that. We pick the solvent which favors alpha attack, sorry, just like ether. And our nucleophile comes in alpha, anomeric effect, solvent effect, pulling in the same direction. We're really favoring alpha attack. Is this the best way to make an alpha thing? No, you probably shouldn't have made an epoxide in the first place if you wanted to do it. But maybe for whatever reason you're stuck with an epoxide. Okay. Um, I'll come back to that. So I'm just having to flip back to find the right reagent for this. There we go. Okay. So we're going to leave glycals for now, and we're moving on to thioglycosides. Thio meaning sulfur. So one of the things that we've been looking at is all these cases. We've had these, whether it was the halogens, which were really, really reactive, these fluorides, which are kind of moderately reactive, and then we had the glycals and the epoxides. The glycals are not very reactive. We can carry those through steps. Once we make the epoxides or the halogen, like the iodoniums and stuff, those are super reactive. But the epoxides are quite reactive. So we all had very reactive things here. We've had these activating groups at the anomeric position that we don't really want to carry through multiple steps. It would be nice if we could put something on there that we could activate at our pleasure, but was stable until we did that. And this is where these guys come in. So we're going to talk about 3 different levels of these. So let's just, for once, I'll draw in the substituents. Again, galactose is my favorite sugar. You can draw that middle one with a dull bond between the sulfur and the oxygen if you like. That's fine. It's correct to draw it as a single bond the way I've done it there. It's correct to draw it as dull bond. It's really both decent ways of saying it. So this is a thioether. Or a thioglycoside. This is a glycosulfoxide. I really suck at these names, so I have my book open next to me so I can look up the different oxidation states of sulfur. I'm okay with those two. This is the one that always gets me. I can never remember sulfones, sulfates, sulfonates. That's a sulfone. So in each of these cases, we have a sulfur attached to 2 carbons and to varying a number of bonds to oxygen. 0 to, well, formally, I guess 2 for the sulfoxide and then 4. Apparently, I need to go back to school to learn how to drink Pepsi. Okay. So what we're going to see here is that reactivity increases as we go down. So what I mean by that is easier to make sulfur fall off. I'm sure there's a more technical way to do it, but that's essentially what we want to do is we want to make the sulfur fall off, make an oxocarbenium, and go to town on it. What this does mean is that these are all reasonably stable molecules. You can actually do a lot of chemistry with the rest of the sugar. And you get to Paul's question of how do I put protecting groups on? Well, you can do a lot of protecting group dances with the sulfur there. And so it's kind of handy to have there because you can get whatever you need on the rest of your sugar, um, and carry these things through. The other really handy thing about this is that we can kind of couple one of these to another of these and do a couple of glycosylations in a row because we can make use of the fact that they're going to react at different rates. And I'm going to show you what I mean by that once we start talking about how we put these sulfurs on, take these sulfurs off, and do some stuff with the sulfurs. Okay. So this is actually one of my favorite sugar reactions there is to just do. Whenever I get depressed, well, actually, one thing I just want to point out is, so let's say we have a free sugar. We'll do a little bit of protecting group chemistry here. Okay, so we know that's an alpha beta mixture because there's mutal rotation, is free going back and forth between the aldehyde and this form. So there's an alpha and a beta. You cannot separate them. They are both there at all times. If I take acetic anhydride and pyridine, so remember what pyridine is, it's that guy. And maybe a catalyst. The catalyst we really like to use for this is dimethylaminopyridine. It is not clear that's a nitrogen. And I heat the crap out of it. I get an acetylation. My major product, much to my chagrin, because I normally don't want the alpha acetate, because the alpha acetate is less reactive than the beta acetate. Let's get the alpha acetate. If I take the same guy, and I take sodium acetate, acetic anhydride. Actually, you don't need heat for that. And I heat the crap out of this. I get mostly beta. Normally do that one on ice. So one's at 120 degrees Celsius, one's at 0 degrees Celsius. Does anyone want to hazard a guess over why you get alpha with the top one and why you get beta with the bottom one? And if you remember what acetic anhydride is, just in case anyone doesn't, it's that. And you all know what sodium acetate looks like. And my camera is not on me, it's like pointing towards my ceiling.
With the first one, with it being at 0 degrees Celsius, you're making the anomeric effect stronger, I think.
Yeah, it's a good way of thinking about it. And I think that is an honest answer. I go to truth of the matter is I go back and forwards on this all the time. So in the first one, your active your base in there is purity and it's cold. So you never have O minus. You always have OH. And your electrophile, especially if you have the DMAP catalyst, is that guy. And it's a damn good electrophile, right? You have a positively charged leaving group on that. So it's a really hot electrophile. And I like where you're thinking. You're kind of thinking, but that equilibrium lies like that. But for the most part, it actually does, remember, it does actually lie mostly beta. For most of the sugars. Like it's not as much as you expect based on cyclohexane ring, but they still favor the beta. So you would expect quite a bit of beta on this. So what we must have here is that these must react at different rates. So the alpha must react faster. And the reason I think you can rationalize that is let's think what happens during these transition states. So let's say it's trying to attack this guy here. So this still has its hydrogen on it. And now we're starting to make a new bond to the acetate. And we're definitely building a delta plus on there. Right? Because we're using our electrons. We haven't lost any electrons. We're using our lone pair to make that bond. And as that delta plus gets stronger, the anomeric effect gets stronger. So this equilibrium here is what happens when those guys are neutral, but they're not neutral in a transition state. The anomeric effect is stronger at the alpha than the beta. And so what you're doing here is you're stabilizing transition state because of anomeric effect. Because in effect, you can delocalize some positive to the ring oxygen. So we can get some of that because of the anomeric effect here. Because this is going to be donating this and donating some electrons here. You're getting some positive charge coming towards this oxygen. So some of the positive that's building up on this oxygen can move to that ring oxygen that's not available for the beta. So that stabilizes this transition state as the reaction is forming.
You mean the oxygen next to the anomeric center, right?
Yeah,
When
this
you say the
oxygen
ring
here,
oxygen? Okay.
ring oxygen, is stabilizing this anomeric reaction. Because you're building up a delta positive here in this transition state, right? Have I lost you?
No, that makes sense.
And so if there's a partial positive here, that means you're weakening this bond. That means you're lowering the sigma star of this bond. So you're making it easier for this oxygen to donate electrons in, which is stabilizing. And it also then moves some of this positive charge over to this ring oxygen. A little bit of a delta plus there. And of course, delocalizing charge is always a good thing. So not only are you strengthening the interaction, you're also delocalizing charge. You got a few things going for you, which is where the anomeric effect is benefiting you here. And that's why you're getting the alpha product with this. Okay. So why does the other one go beta? No sterics. Okay, I do like that. I actually agree with that. Um, I think it is partially and quick SN2. Right, the beta is normally more reactive than the alpha. Which actually, I'm not quite sure if the quick SN2 follows from that. But I think the thing to remember is you're really, really hot. And so I think there's two explanations for this. And again, I don't know which one's right. One thing is, let's consider that under these conditions you have so much heat that it is not unreasonable to think that you have a non-negligible amount of O minus there. And that's been deprotonated by sodium acetate just coming in and grabbing a hydrogen. Now, the anomeric effect is really not operable now because holy shit, this guy does not want to accept more electrons. It is already O minus. So I think we've already seen this example. Negs sit equatorial. And we're going to see this again in a couple classes. And the second one is, so I think, so you have more of this, and also, in general, anomeric effect be damned, not present, equatorial is faster than axial. Equatorial nucleophiles react faster than axial sterics. It's just a simple argument of sterics. It's just that has a lot more space around it to attack things. There's more angles and possibilities for the acetic anhydride to bump into that for the nucleophilic attack than there is for the more crowded alpha one. I'm happy with either of those explanations. The other explanation I'm happy with, I don't know if any of you have gone back and read the papers I put up about the anomeric effect, is that, again, big argument over whether it's a kinetic or a thermodynamic process. But under these energies, we have so much energy in the system that kinetic product distribution is not really going to come into it. Now we're under pure thermodynamic product distribution. So even if we made a mixture of these two, the sodium acetate is going to be doing SN2s all day long. Less sterically hindered. I'm not sure how much I buy this argument. I go back and forwards on this because I think, well, shit, it kind of goes against everything else I'm saying with everything. Where we're saying the anomeric effect is a nice, strong thing that drives the formation of the alpha product, and beta substituents are much more reactive than alpha substituents, which inherently means that they're less stable. So I'm saying it is both more stable and more reactive, which makes no fucking sense. So, but I've seen this argued that because this is less sterically hindered, you favor the beta. I don't like this argument as much. I prefer this one, that the reaction just occurs from the equatorial site, but it does require it being O minus. And I definitely agree that the O minus will be much more reactive than the OH, and if there's enough energy in the system, but it's still going to be very, very small because sodium acetate is not a very strong base. So I'm very much on the fence over how to explain this.
If you were to do this at low temperature, would you just get a racemic mixture?
If you do this at low temperature, you get no reaction.
Okay.
Nothing fucking happens. Yeah, you need a stronger base. Then you need pyridine or some sort of strong nucleophile. Sodium acetate, acetic acid doesn't do anything. You actually mix these things together, and you basically take solid sugar, you dump it in, you dump in like a pile of sodium acetate, which is a solid, and then you pour some acetic anhydride on top, and then you have like a lot of solid and a little bit of liquid floating on top. Then you desperately try to get a stir bar stirring in there by messing around with your magnetic stirrer, and eventually it gets moving, and then you start heating it, and then it starts going black. And I don't know why it goes black, but it always goes black. Black isn't a good color normally in chemistry. Normally it means your stuff is turning into tar. This always goes black. Um, and then the reaction occurs. And, doesn't
At
take
what
very long.
at what point do you stress cry?
The first time I did it, I stress cried very early, but after that, you just get used to it and it works pretty well. This is a very clean reaction. It's one of these nice things. You have this black tar that comes out of it, and then you get like a 95% yield of white crystal after you crystallize. It's beautiful. Okay. It's chemistry. It's lovely. You never stress cry.
You only cry because your reaction is so beautiful.
Yeah, that's why I'm crying. Okay. So let's go back to this acetate. So now we made our beta acetate by taking sodium acetate. Mostly protection group stuff isn't really that complicated. This one's the one that's pretty tricky, actually, is the sugars with the peracetylation because of what's going on at the anomeric center. Most of the time, we have something at the anomeric center, something that we stuck on. Like any of these things that we're doing, we're putting that in. So all the protection group stuff we're going to talk about is C2 through C6. So we only got 4 hydroxyl groups to protect selectively, which isn't as much of a nightmare as 5. And because most other protecting group strategies are just a mess over what they do with the anomeric center, but we can control which one we get using the acetate. So we take this. I love this reaction. BF3 etherate. So this is our nice strong Lewis acid. And thiophenol, which stinks really badly, and you bleach everything. But it works beautifully. This is like 99%. There aren't a lot of reactions which are 99%. Most of the glycosylations we're doing these in this course, I'm pretty happy if we manage like a 60% yield on them. This guy works really, really well. So we can do this. Another way we can make those is, let's say, for whatever reason, we had a bromide at that position. We can use the sulfur salt. Maybe you just don't want things to stink because these sulfur sodium salts don't smell like anything. They're kind of nice. I did that top reaction a lot in my PhD, and so I went home to my now wife every night, and I smelled like rotten eggs. I was very popular. We had a very small apartment, so I slept on the floor sometimes. So we can do SN2 chemistry directly on the bromide. Then we've got a few other options on how to go about doing this. Um, we can actually start with. Let me make sure I do this right. Yes, I'm going to. We can actually start with the OH. This has never worked as well in my hands. People promise that it works amazing. I don't really believe them. This is thiourea. It's like urea, but with sulfur instead of oxygen. I'm going to leave the mechanism as an exercise. And you're going to get the S minus equatorial for obvious reasons because negative things like being equatorial. All I can say, I'm going to point out that this does go through the aldehyde. So you're going to use the aldehyde version of this for the mechanism. And then you can treat this with any alkyl bromide that you choose to use. So that gives you a lot of flexibility if you don't want a phenyl group there, if you want something else. We use the phenyl group a lot. I'm going to basically use it exclusively in here. You will see the thioethyl a little bit. The reason we use thiophenyl is for all that smells bad, the rest of them smell worse. And that's actually, I think, literally the reason why we use thiophenol so often is it doesn't smell as bad as all the other thiols. But yeah, but you can use basically anything. There's nothing really special about having an aromatic group there. An alkyl group works just fine. And almost all this chemistry works just as well with thioethyl as it does with thiophenol. So we can make these thiols now, thioglycosides, and like everything else, we're going to want to use them. So the nice thing about them is, unlike all the other groups we've talked about here, they're really resistant to most reaction conditions. Like you can do all sorts of crazy shit to the rest of your molecule, and the thioether is going to sit there. Like there are thioethers all over the place. They're stable. Like methionine's a amino acid, right? And it's a thioether, and isn't okay. It's not the best amino acid. It does tend to oxidize on you when you're not looking, but for the most part, it behaves itself. And we'll spend some time talking about methionine oxidizing on us when we're not looking in the second half of the course. But if we have a thioether and we do want to react it, and let's say we have acetate protecting groups, there are certain ways to do this quite well. The best one is using NIS and triflic acid. So note that we need NIS on its own, which is a strong iodinating agent. I consider it very reactive, is not sufficient to activate a thioether. You need to add the strong acid. So what is going on here? Well, NIS, if you remember, or not, that's okay too. I suck at names, so I'm really, really sympathetic to other people who suck at names. NIS is that. Looks pretty good. That iodine looks pretty electrophilic, because I can use the nitrogen iodine bond and put them into resonance with the oxygens. So it's kind of like a source of I plus. And so many conditions, that is the source of I plus. That's great. For this guy, we need to add a really strong acid, triflic acid, like the strongest acid, to activate this. So what happens here is you add some triflic acid. It does what you think acids are supposed to do, which is protonate something. And oh, Molly, does it protonate this. It's triflic acid after all. It's going to protonate everything. Now you just made that iodine a whole lot hotter of an electrophile, because not only now are you donating electrons in to make some resonance and stick an O minus on, you're now going to make an OH. You're going to make a neutral oxygen. So in this case, you've now made this hot. Now it's hot enough. So what you might say, I've just made that. Well, sulfur and iodine makes a pretty strong bond, because I actually have no idea why. Like, yeah, they're closer on the periodic table than oxygen and iodine or nitrogen and iodine, but any two heteroatoms attached together just seems like a bad idea to me. This is why I'm not a physical chemist, because it doesn't seem like a bad idea to them. Because in reality, it's not a bad idea. So my intuition is just shit. And, you know, we're set up to make an oxocarbenium. That's a really good leaving group. And now we make chimeric assistance because it's an oxocarbenium. And everything just behaves kind of like an oxocarbenium, where we spent quite a lot of time talking about them with the bromide. So I'm not going to waste any more time here. Nucleophile. Comes in. Product goes out. There aren't actually a lot of ways to activate this. You do have some options. So instead of NIS, you can use the NIS TFOH, or you can use, not really all that excited actually, TMS triflate, which is basically the same thing, except you switch to silicon group for a hydrogen, but still really strong acid. Or you can use NBS TFOH or NBS TMS triflate, and that's about it. These guys are pretty resilient to most conditions. So if you're not tossing these reagents at this, like you're just using NIS on its own or just TMS triflate on its own, the thio ether just stares and goes, yeah, whatever, I don't give a shit. Like, you need to combine these things. So if you're not using these reagents, your thio ether is really not going to do anything. It's going to behave itself. So it's nice and selective because you can do a lot of other chemistry, because most chemistry does not involve these pairs of reagents. It's a rather small sampling of chemical space here. Oh, there's one other one you can use. Bromine or iodine and silver triflate. So again, really weak silver triflate bonds. Silver plus. Silver likes its halogens, so silver is going to strip away an I minus or a Br minus, which will leave you with a Br plus or an I plus, which will do the same thing as the NIS or MBS. So it's another way to get I plus or Br plus. It's really reactive I plus or Br plus. But there's not a lot of options here. So I'll toss in basically everything that's out there. IDCP, which we saw with the ionation, will do it too, because that is naked I plus. But there's not a lot of yeah. I'm gonna repeat myself and say there's not a lot. I think I'm gonna end today right there. We're gonna pick up sulfoxides and sulfones next class. We're gonna see them used in making some disaccharides, and we're gonna sort of talk again about this concept. I think we talked about lecture number 2, which was armed and disarmed donors, and we're going to discuss that in terms of these sulfoxides as an example. So I think I'm going to call it there because it is 5:20.
Could you go back to the previous slide real quick?
Yeah. And I'm going to post these slides immediately. I posted assignment 2 and assignment 3. I don't think you can do assignment 3 yet. You can do most of assignment 2. You can do all of assignment 1. Remember, the midterms are going to be based on these. I would start looking at them. I think that most of these questions, there's no one right answer. There's multiple right answers, and we're going to kind of think about these on their own, try and come up with the answers to this stuff. If you need, if you do need to be pointed in the right direction for some of the questions, email me, and I'm happy to set up some office hours.
Well, I know me, Samara, and Susanna were tossing around some ideas. Do you want me to just email for the review? Do you want me to just email our thoughts or of what we want to do?
Yeah. If you guys have come up with something that you want to do.
Okay.
Yeah. Are they assigning you the communication captain?
No one's assigning me it, but I guess it's just how it happened.
Okay. Well, I assume they're okay with what you tell me about. So just CC. We'll make sure that everyone's CC'd on all the emails.
Okay, yeah, I'll just.
Everyone is clear on what we're agreeing to.
Cool. Yeah, I'll just email that right now.
Yeah, because we had a couple ideas. We're just being indecisive.
Okay, well, do you want to talk about that now?
Oh, yeah.
We're done the lecture, so we've got 10 minutes. I'm just going to stop recording.